It's my absolute pleasure to introduce Chris Bishop. Chris Bishop is a Microsoft Technical Fellow. He also is the Managing Director of our Cambridge Research Lab. He's also a Professor of Computer Science at the University of Edinburgh and a Fellow of the Darwin College, Cambridge. In 2004, he was elected Fellow of the Royal Academy of Engineering, and in 2007, he was elected Fellow of the Royal Society of Edinburgh, and in 2017, he was elected as a Fellow of the Royal Society. There is a long list of achievements and accolades that I can go on talking about, but I'd rather let Chris's talk do the talking. I'm sure he won't disappoint. So without much further ado, Chris, all yours. Yeah.
Thank you very much. Thanks for the invitation to come here. It's a great privilege to be the final speaker. I thought what I'd do for this talk is, rather than talk about any particular application or particular algorithms, is to step right up to 50,000 feet and think about machine learning and what it is all about, what are we trying to achieve, and in particular to give you a perspective on machine learning that I call model-based machine learning, which you can think of as a compass to guide you through this very complex world. So machine learning can be very intimidating. There are many, many algorithms. Here are a few. Every year at NIPS, hundreds more are published. You've heard about lots today. And especially if you're a newcomer to the field, it's bewildering, it's intimidating. Which ones do you need to learn about? Which ones should you use for your application? It can be really challenging. So model-based machine learning is just a perspective that I hope will help guide you on your journey through machine learning, whether you're working on new algorithms or in particular whether you're working on real-world applications. So going back to all of these algorithms, you might be a little frustrated and say, why do I have to learn about hundreds or thousands of different algorithms? Why can't these machine learning people just come up with the one universal algorithm? In fact, maybe they have. Maybe it's deep neural networks. Perhaps deep neural networks solve all of humanity's problems, and I don't need to learn about the rest. Okay. Well, there's a theorem, and it's a mathematical theorem. It's proven, so it's unlikely to be retracted any time, and it's called the no free lunch theorem, and it's attributed to Daniel Wolpert back in 1996. And it says that averaged over all possible data generating distributions, you can think of that as averaged over all the possible problems you could ever want to solve, every classification algorithm has the same error rate when classifying previously unobserved points. That means if an algorithm is particularly good at one problem, it will be particularly bad at some other problem. Put it another way, there is no such thing as a universal machine learning algorithm. Now, this is not my personal opinion, it's a mathematical theorem. Or to put it another way, the goal of machine learning is not to find the universal algorithm, because it doesn't exist, but instead to find an algorithm that is, in some sense, well matched to the particular problem that you're trying to solve. Okay, so this is very fundamental, at the very heart of machine learning. So machine learning, we all know, depends on data. But we cannot learn just from data. We need to combine data with something else, with a model. Or we can think of this as constraints, or we can think of it as prior knowledge. I'll use the term prior knowledge, but people call it lots of different things. You cannot learn from data alone. Otherwise, we'd have a sort of universal algorithm. So we need to combine data with this prior knowledge in order to make any progress. Now, we also know, and particularly from the recent developments in deep learning, that the more data you have, the better. And in some sense, if you have lots of data, you can get away with a little bit of prior knowledge. Or conversely, if you're in a world where you have very limited data, then you need to complement that with a lot of prior knowledge, very strong assumptions about the problem you're trying to solve. Now, what's interesting is the meaning of this vertical axis. What do we mean by a lot of data? So this is a really important point. So I want to talk about big data and what we mean by the size of a data set, because there are two completely different meanings to the size of a data set. And it's very important not to get them confused. There's the computational size, which is just how many bytes does it take up on disk. And there's the statistical size, which relates to its information content. So we'll illustrate this with a couple of sort of corner cases. So the first example, imagine we have a block of metal. We apply a voltage, and a current flows through the block of metal, and we're going to measure how much current flows when we apply a particular voltage. And we've got 7 measurements here, so we've applied 7 different voltages, and we've measured the corresponding values of current. And our goal is to generalize. This is a machine learning problem, and so our goal is to predict the current for some new value of voltage on which we haven't yet made a measurement. Now, in this case, some kind and friendly physicist has come along and told us about Ohm's law, and Ohm's law just says current is proportional to voltage. It's a straight line through the origin. The only thing we have to learn is the slope. The data points, as I've shown, have measurements. These are have measurement errors. These are real-world measurements. They're a little bit noisy. If they weren't noisy, one data point would determine the slope exactly. But the data points are noisy, and there's only a finite number of them, and so we don't know the slope exactly. But if we've got 7 measurements and the noise is not too high, we can be pretty confident about that slope. There's not very much uncertainty. This is a data set which is computationally small, because it's 7 pairs of floating point numbers, so computationally it's a tiny data set, but statistically it's a very large data set. In other words, if I gave you another 1,000,000 measurements of current and voltage, then your uncertainty on the slope would get a little bit smaller, but it's already very small. So the next 1,000,000 data points are not going to make a lot of difference. You're already in the large data regime from a statistical point of view. Think about another corner case. Imagine we're going to have some images, and we're going to label the images according to the object that they contain. So it might be airplane, car, and so on. And these images might have millions of pixels. They're occupying many, many megabytes each on your disk. And we might have 1 billion images of each class, 1 billion examples of airplanes, and 1 billion examples of bicycles. So this is going to take up a huge amount of disk space. So this is a data set which is computationally very large, big data in the usual sense. But what about statistically? Well, let's imagine I'm naive and I just treat these images as vectors and feed them into my favorite, whatever, neural network as a classifier. If you think about the aeroplane can be anywhere in the image. That's 2 degrees of freedom. Actually, it can be any distance as well. So 3 degrees of freedom of translation, 3 degrees of freedom of rotation. The airplanes can come in different colors, different shapes, different illuminations. And all of these degrees of freedom can be taken together combinatorically. So the number of, if I showed you one image a second, and you all agreed that every image was an aeroplane, how long before I run out of images? Well, the answer is far longer than the age of the universe. I mean, the number of images that we would all agree are aeroplanes is vast compared to the number of electrons in the universe. So if you just have a very naive approach to classifying these objects, then even 1 billion images of each class is a tiny, tiny data set. So it's a computationally large data set, but statistically small. So I'll just go back for a second to the previous picture. This refers to not to the computational size of the data, but to the statistical size. Okay. So that's the concept of prior knowledge and data, and the concept of the size of the data set. So coming back to this problem then of which algorithm am I going to use? How am I going to address this problem of just thousands and thousands of different algorithms? So I want to introduce you to the philosophy, if you like, of model-based machine learning. But it's a very practical philosophy. So the idea of this is not to have to learn every algorithm there is, and it's not to try out every algorithm and empirically see which works best. The dream of model-based machine learning is instead to derive the appropriate machine learning algorithm for your problem, essentially by making this prior knowledge explicit. I'll show you how that works in a minute. So traditionally, we say, how do I map my problem onto one of these standard algorithms. And often that's not clear, and so typically people will try out lots of different things. They'll try out decision trees and neural nets and support vector machines and so on and so on. Instead, in the model-based view, we say, what is the model that represents my problem? What is the model that captures my prior knowledge? And so by forcing ourselves to make these prior assumptions explicit, we have a compass to guide us to the correct algorithm, or at least a set of algorithms. So the idea is the machine learning algorithm is no longer the first-class citizen. Instead, it's the model. It's the set of assumptions, and those set of assumptions are specific to the problem you're trying to solve. So for your problem, you'll have one set of a set of assumptions. You'll have a different set of assumptions. You will arrive at different algorithms, and that's why there's no such thing as a universal algorithm. It's the algorithm that's tuned to the particular problem you're trying to solve, and that's reflected in this domain knowledge, these assumptions, this prior knowledge. So we take the model, the prior knowledge, and we combine it with an inference method. And the inference methods tend to be fairly generic. So the inference methods will be things like gradient descent, perhaps for neural nets, or expectation propagation if we're looking at graphical models. General techniques for optimizing or computing the posterior distribution of parameters of our model, and together they define the machine learning algorithm. So the dream is you write down explicitly your assumptions, you choose an appropriate inference method, and then you derive the machine learning algorithm. And when you apply it to your problem, it will be wildly successful. So that's the dream. Now, we're not entirely there yet, but I'll show you some great examples. Let's talk a little bit about the assumptions that go into models. You look at deep neural nets, you think, well, they're not making any assumptions. They're just generic, universal machine learning algorithms. You pour data in one end and magic comes out the other. So where are the assumptions in a neural net? So let's look at, if you like, the simplest neural net algorithm, I suppose. It's logistic regression. This is making a very, very strong assumption. This is a lot of prior knowledge. That prior knowledge histogram is sort of, it's high, because it's restricting us to a very, very narrow domain. It's making very strong assumptions. It's saying that the prediction Y is some linear combination of the inputs passed through some sigmoidal nonlinearity. So that's a very, very specific model. And if we have multiple outputs at the same time, then we arrive at a single layer neural net. That's like lots of logistic regressions happening all at the same time. And that, of course, was the type of model that was very, people got very excited about in the first wave of neural nets in the days of the perceptron and so on. The second wave of excitement of neural nets in the late 1980s, early 1990s, was when backpropagation came along. We learned to train two-layer nets in which these features themselves could be learned from data. And it was a very exciting time. I actually made a crazy decision, which was to abandon what was a very successful career in physics, because I'd read Jeff Hinton's paper on backprop, and I thought, wow, machines that can learn, artificial intelligence, this is the future. And I gave up my career. I persuaded my boss to buy me a computer. I taught myself to program, because I'd never done that before, got some C code, and started hacking away. So that was the second phase of excitement around neural nets. Then, of course, they went away again. And they didn't really go away. They became rather niche. People moved on to other things. So support vector machines were very popular for quite a while. And then along came deep learning, where we learned how to train many, many layers. That's deep learning. And by the way, the story I heard from Jeff, I don't think he'll mind me telling you this. He was very fed up, of course, because he had discovered backpropagation with colleagues, and they'd been quite successful. But then they were overshadowed by these support vector machines, which is kind of a funny sort of approach to machine learning in a way. And so when he finally got neural nets to work properly, he decided to call them deep learning, because that allowed him to call support vector machines shallow. That's the real reason. Okay, so what prior knowledge is built into this? Well, again, there's a lot of prior knowledge. It says the output is determined by this hierarchy of processing. So let's take a problem. Let's imagine I'm going to take a photograph, and I'm going to classify that image as either happy or sad. Now, what does the computer see? The computer sees pixels. So how does a deep neural network solve it? Well, the deep neural net, at the first layer, what it's doing is looking for things like contrast, dark regions next to light regions. And the next layer, it can combine those local contrast detectors to detect rows of pixels in the image in which effectively you have an edge, a dark region separated from a light region. Maybe the next layer looks where edges end or where they change direction, so it looks for things like corners. And a little bit further up, the corners get combined together to make shapes, things like faces, perhaps expressions on faces, objects that you see in the image. Maybe the next layer up, it's looking at the relationships between objects. Maybe there's a birthday cake, maybe there are candles, maybe there are people, maybe the people have smiles on their faces. Maybe at this point you've got a lot of evidence that this is a happy image. And our brains are like that too. They have this layered processing. They have center surround response, oriented edge detectors, and so on. And when we train artificial systems, we find similar structures in the layers of visual processing that we find in the brain. So there's one very strong piece of prior knowledge built in, which is this hierarchical processing. And it seems to be very effective. So what's really going on, the reason deep learning is working so effectively, another way of saying this, is that there are lots of problems in the world, including the image processing example I just gave you, where this hierarchical structure seems to work well on real applications. Or put it another way, the prior knowledge that's built into these deep networks resonates well with the kinds of problems we're trying to solve using these networks. So let me say a little bit about then data and prior knowledge. And we'll look at some of the other assumptions that are built into neural nets. So let's imagine now that I've got an image, a set of images, and my goal is to classify the images according to whether they contain a person or they don't. So here's an image, and this image does contain a person. And what we know is that that classification does not depend on where in the image the person's located. So these are all examples of images that contain a person. Now, in terms of the vector of pixels, they're all very different, but they all belong to this class. If I want to build a system that can detect a person, irrespective of where the person is in the image, then one way to do it is to go and collect huge numbers of images with people at all possible locations. And then the system will learn that they're all examples of people. The challenge there, of course, is a bit like that aeroplane, this very high-dimensional space, the aeroplane example. I need many, many examples, lots of examples of images, just to capture this notion that the classification doesn't depend on location. So it's very sort of wasteful of data. Another way of doing it is to generate synthetic data. So maybe I don't have data of people in lots of locations, but maybe I've got just one image of a person in one location. I can create synthetic data in which the person is moved around into different positions. So that's another way of building prior knowledge, not building it into the model, but effectively augmenting the data. And that's quite commonly used. Again, though, it's quite wasteful because I have to replicate the data set, so I end up with a computationally large data set. It would be much smarter if we could just give it one example of a person, and then in the model, bake into it the prior knowledge that the output doesn't depend upon location. So we call that translation invariance. And the way we do that in neural nets is through convolutional neural networks. So this is the input image, and we have a convolutional layer. In the convolutional layer, each node looks at a small patch of the image. The node next to it looks at the next small patch, and then the weights between the blue node and the red node are shared. So they can adapt during training, but they're always in lockstep. So whatever this blue node learns to detect, the red node will detect exactly the same thing, but moved slightly. Okay, so that's the convolutional layer. That's followed by a subsampling layer. Again, this node looks at a small patch on the convolutional layer, and it might do something like take the max. So imagine there's something in this image which causes the blue node to respond, and that causes this node to respond. Now we move it slightly. Now instead the red node will respond, but again, because we're doing something like a max, this will still respond. So this now exhibits translation invariance. It responds even though the image has moved slightly. Now what we do in practice is we repeat this many times. We alternate between another convolutional layer, another subsampling layer, and it's subsampling because the resolution of this is lower than that, And eventually, when we get to the output, we have a few outputs, and we have translation invariance. So as we move things around in the inputs, the outputs stay the same. This actually encodes a sort of more general kind of translation invariance, because imagine part of the input is translated and not the other part. Again, the output will be invariant. So it's exhibiting sort of local translation invariance. Think of a rubber sheet deformation. Imagine I've got that birthday party, and some of the people move around, and the birthday cake stays where it is. It's still a happy scene. So we've got sort of local as well as global translation invariance. So you can see this is not a universal black box. This has got a lot of strong prior knowledge baked into the structure of the network. And if you don't have those sorts of structures, good luck with classifying aeroplanes and all the rest of it. You're back in that exponential space again. Okay, so summarize where we've got to so far then. We've talked about the fact that there is no universal machine learning algorithm, that the goal is to find an algorithm that's good on the particular data set that we have. That depends upon combining the data with prior knowledge. And the dream is that by being explicit about the prior knowledge, combining it with an inference algorithm, we'll discover the machine learning algorithm instead of having to read 50,000 NIPS papers, implement them all, and compare them all. I want to introduce another concept now in machine learning. So machine learning, as you know, this particular, the sort of breakthrough of deep learning has generated this tremendous hype and excitement around artificial intelligence. Now, artificial intelligence, you know, the aspiration goes back certainly to Alan Turing 7 decades ago, and you know, the goal is to produce machines that have all of the cognitive capabilities of the human brain. It's a great aspiration, and we're a very long way from achieving it. We've taken a tiny step towards it with the recent developments in machine learning. So does that mean that all this hype about artificial intelligence and all the excitement and the billions of dollars of investment is all a waste of time because it's all decades and decades away? In my view, no. In my view, all of the excitement around machine learning is totally justified, but not because we're on the brink of artificial intelligence. We may be not. Maybe it's centuries away, or maybe it's next year. I have no idea. But there is something happening which is revolutionary. It's transformational. And it's the transformation in the way we create software. And I'm not really talking about the development process. I'm talking about the fact that ever since Ada Lovelace programmed the analytical engine for Charles Babbage, she had to specify exactly what every brass gear wheel did step by step. And software developers do the same thing today. It's a cottage industry in which the developer tells the computer exactly what to do step by step. Now today, of course, the developer doesn't have to program every transistor. They'll call in some API which invokes 1 million lines of code written by other developers, and there are compilers and data machine code and all the rest. So they're very effective, very productive compared to Ada Lovelace in terms of their efficiency, their productivity. But fundamentally, we're still telling the computer how to solve the problem step by step. Now, machine learning, we're doing something radically different. Instead, we're programming the computer to learn from experience, and then we're training it with data. The software we write is totally different. And the software we write often has a lot of commonality. So we'll use neural nets to solve speech recognition problems, computer vision problems, and so on, adapted each time according to the prior knowledge of our domain, of course. But we're doing something radically different. So I think this is a transformation in the nature of software, which is every bit as profound as the development of photolithography. So photolithography was a singular moment in the history of hardware. Ever since the days of Charles Babbage and gear wheels, vacuum tubes, transistors, logic gates, computer hardware has been getting faster and cheaper. And then we discovered how to print large-scale integrated circuits using photolithography, and it was a transformation because it went exponential. So that's Moore's law. We learned to print circuits, and now the number of transistors on a circuit doubles every 18 months. And as they get smaller, they get faster. Amazing things happen. That's why we have the tech industry. That's why we're all carrying supercomputers around in our pockets, because of photolithography, because of Moore's law. Something interesting may be happening in software, because the way we're creating these solutions is by programming the computer to learn from experience and then training it using data. And we're now seeing a Moore's law of data. The amount of data in the world is doubling maybe every year or two. And so we are on the brink of something tremendously exciting and all-pervasive through machine learning. That's real, that's happening right now. One of the things that it might lead to is artificial intelligence. But even if it doesn't, or even if artificial intelligence is decades away, this is going to transform every aspect of our lives. And one of the areas that I'm hoping it'll transform is healthcare, and that's a personal interest of mine, but it will be all pervasive, and I do think it's transformational. I've got the yin and yang diagram because I think there's a kind of flip side of learning from data, which is quantifying uncertainty. So again, go back to traditional computer science, it's all about logic, it's all about zeros and ones, everything is binary. The engineers at Intel and ARM work really hard to make sure every transistor is unambiguously on or off. When we're in the world of learning from data, we're in the world of uncertainty. We have to deal with ambiguity. So uncertainty is everywhere. Which movie does the user want to watch? Which word did they write? What did they say? Which web page are they trying to find? Which link will they click on? Which gesture are they making? What's the prognosis for this patient? And so on. In all cases, we never have a definitive answer. We're never certain which link the user's going to click on, but they may be much more likely to click on one link than another, and we can compute that likelihood using machine learning. So uncertainty is also at the heart of machine learning. So again, there's a transformation from logic to thinking about uncertainty. And of course, as you all know, there's a calculus of uncertainty, which is probabilities. And again, there are mathematical theorems which show that if you're a rational person and you quantify uncertainty, you will do so using the rules of probability or something that's mathematically equivalent to them. So again, that's a mathematical foundation that's laid a long time ago. That's not going to change. But it's worth thinking about, just very briefly, two perspectives on probability. What do we mean by probability? Well, when we're in school, we usually learn a little bit about probabilities. We learn the frequentist view, the limit of an infinite number of trials, a frequency interpretation of probability. But I'm sure many of you know there's a much broader interpretation, which is probability as a quantification of uncertainty. And that's the Bayesian perspective. In fact, it's almost unfortunate that they're both called probability. But the mathematical discovery is that if you quantify uncertainty using real numbers, those numbers behave exactly the same way as the frequencies with which dice throws behave. And so we've called it probability. And the fact we use the same name for both, I think, has caused a lot of confusion over the years. Let me just give you a little example. Hopefully this will shed some light on this. So imagine we've got a coin, and the coin is bent. So the coin is not equally likely to land one side or the other. We'll imagine if I flip the coin, there is a 60% probability it will land concave side up and a 40% probability it will land concave side down. Let's just imagine that's the physics of this particular bent coin. What do we mean by 60% probability? We mean if we flip it many times and compute the fraction of times it lands concave side up, as we go to the limit of an infinite number of trials, that fraction, which will be a sort of a noisy thing, it'll settle down, it'll asymptote to some number, and that number will be 0.6. So that's the frequentist view of probabilities. Now let's suppose that one side of this coin is heads and the other side is tails. But imagine you don't know which it is. Okay? All you know is that the coin's bent and there's a 60% probability of landing concave side up. Okay, so Victor, I'm going to make a big bet with you, and $1,000 about whether the next coin flip's going to be heads or tails. Now, you're a very rational and very intelligent person, so how are you going to bet? You're going to bet 50-50. It's sort of obvious, right? It's symmetry. Victor doesn't believe that that if we repeat the experiment many, many times, that half the time it'll be heads up and half the time it'll be heads down. What he believes is that it'll either be 60% heads or it will be 40% heads, assuming we're flipping the same coin each time, but we don't know which it is. So the frequency with which it lands concave side up, that's like a frequentist probability, but our uncertainty about whether the next coin flip is going to be heads or tails is like a Bayesian probability. And so imagine I've got this bent coin behind the desk here, and I'm flipping the coin, and I'm honest and truthful, and I'm telling you whether it's heads or tails. The more data you collect, the more you can discover about whether heads is on the concave side or heads is on the convex side. So as you collect data, your uncertainty about whether the heads is concave or convex, that uncertainty gradually reduces. And in the limit of an infinite number of trials, there's no uncertainty left at all. You're completely certain about which is concave and whether the heads is on the concave side or the convex side. But you still don't know whether the next coin flip is going to be heads or tails. But let's say you're certain that the heads is on the convex side, then you know there's a 60% probability the next flip will be heads. I hope that illustrated the difference between Bayesian and frequentist probabilities. That's the simplest example I can think of. At this point, you might be thinking, why am I making so much fuss about this? Because I've said that in traditional computing, everything is 0 or 1, and now everything is going to be described by probabilities which lie between 0 and 1, and it seems like a tiny change. It seems like just a little tweak. So this is an example. This is my illustration of why it's not a little tweak, why it's a profound difference. So imagine here's a bus, and let's suppose the bus is longer than the car, and we'll suppose that the car is longer than the bicycle. Okay, now again, you're all smart people, so if I say the bus is longer than the car, and the car is longer than the bicycle, do you all agree that the bus must be longer than the bicycle? Okay, if anybody doesn't agree, go back to the beginning of the class or something. That's a very well-known property. We call it transitivity. And here's the amazing thing. When we go to the world of probabilities and uncertainty, transitivity need no longer apply. And there's a really simple example of it. And it's these things. These are called Efron dice, or non-transitive dice. And they're standard dice, except they have unusual choices of numbers. And let's say, again, I'm determined to get some money out of Victor, so I'm going to make a bet that we're going to have a game of dice, so we're going to roll the dice 11 times, some odd number, and whoever gets the greatest numbers of wins is going to get the money. Well, it turns out that the orange die will beat the red die 2/3 of the time. So 2/3 of the time, the orange number will be bigger than the red number. Big deal. If I play the orange against blue, 2/3 of the time, blue will give a bigger number than orange. 2/3 of the time, green will give a bigger number than blue. And now here's the amazing thing. The bicycle is also longer than the bus, because 2/3 of the time, green will give a bigger number than red. Now, if that isn't counterintuitive, I don't know what is. It's bizarre, right? It's extraordinary. And it's just a consequence of the fact that these are uncertain numbers. They're stochastic numbers. And the way it works is actually very simple. So these are the numbers on the different dice. So the orange one actually always rolls a 3, as it happens. On the red one, 2/3 of the time you get a 2, and 1/3 of the time you get a 6. So it's obvious then, 2/3 of the time, orange gives you a bigger number than red. And I'll leave it as an exercise for you to check the others. And occasionally, in my copious spare time, I sometimes go and give talks in schools to sort of try and inspire the next generation with excitement of machine learning, artificial intelligence, computer science. We actually hand out packs of these dice to the kids. And if you go to that link, you can actually read a little bit more about it, and you can see those numbers and check for yourself this is real. So again, I think this is quite a profound shift from the world of logic and determinism to, if you like, the real world of uncertainty. At this point, I was going to show a demo, and sadly, I can't show you the demo. So in fact, I'm just going to skip over this. Let me recommend a demo. OK. The demo was simply an example of machine learning in operation, where the machine learns about my preferences for movies, and it actually does so in real time. So as I rate movies as like or dislike, its uncertainty about which movies I like gradually reduces. So what you're seeing in the demo is really, if you like, the modern view. I like to call it the modern view of machine learning, not machine learning as tuning up parameters by some optimization process, but instead machine learning in the sense that the machine has a model of the world, in this case a very simple world, the world of movies that I like or don't like. It has uncertainty about the world, expressed as probabilities, and as it collects data, that uncertainty reduces because it's learned something, rather like the coin flip example. And we can think of all of machine learning from that perspective. What I'm going to do now is give you a tutorial in about one slide on a favorite subject of mine, probabilistic graphical models, because I'm going to show you how we're taking steps towards realizing that dream of model-based machine learning, not just as a philosophy of machine learning, not just as a compass to guide you through this complex space, but even as a practical tool that we can use in real-world applications. And to do this, I'm just going to need to give you a very quick tutorial on graphical models. If you know about graphical models already, this will be very boring. And if you don't know about graphical models already, you're probably going to learn too much, but at least you'll get a sense of it. So imagine I've got two boxes. One of them is green, one of them is blue. And I'm going to pick one of these boxes at random, but not necessarily with a 50-50 probability. It might be 60-40 or something. And I'm going to describe that by a graphical notation. And this graphical notation, I have a circle representing this uncertain quantity. So it's the value jar. So jar is a binary variable that's either green or blue, but it's not a regular variable. It's not either green or it's blue or it's nan or something. It has a probability of being green or blue. It's an uncertain variable. And this little box just describes that probability. Now imagine that the boxes contain cookies, biscuits, as we say, and these biscuits are either circular or triangular. And the proportion of biscuits is different in each box. So I can now say, supposing I go to the green box, the green jar, and I pull out a cookie without looking, then there's a 1/3 probability that it'll be triangular and 2/3 that it'll be circular. If I go to the blue jar instead, there's a 1/3 probability it'll be circular and 2/3 that it'll be triangular. Okay? So again, there's some uncertainty. If I draw a cookie out of the jar, we're uncertain about which it is, but we know something. We know this probability. And so cookie, again, is an uncertain variable that's either triangle or circle. It has some probability, but the value of that probability depends upon the value of this random variable jar. So we can think of this model in what we call a generative way, in which I do an experiment. I, first of all, randomly choose a jar, and then given that jar, I dip in and I randomly choose a cookie, and that tells me the value of jar and consequently the value of cookie. That's a forward model, and that generates data. It generates jars, it generates cookies. And I could repeat that many times. Now, in real applications, typically, and this graph, of course, is describing my prior knowledge about the world. I know that the world consists of jars and it consists of cookies, and they relate to each other in certain ways. So this graph is a very visual way of expressing that prior knowledge, which is obviously critical in, as we've seen, in machine learning. Typically what we do, though, with these graphs is we observe something. In this case, we might observe cookie, and we want to go the other way. We want to work out which jar did that cookie come from. So maybe there's a 60% chance that it's green, so it's more likely to be green. But now when I observe the cookie, I observe that the cookie is triangular. Now your intuition says, if it's triangular, it's more likely that it came from blue than green. And that's correct. And when you run the maths, which is called Bayes' theorem, very simple, you'll find that the probability that it was jar shifts a little bit towards blue, just as your intuition would expect. And so that, if you like, is the machine learning process. We've observed that I like a particular movie, and the internal state of the machine gets updated using sort of Bayes' theorem on steroids to say, actually, I'm a bit more likely to like action-adventure than romantic comedy or whatever it might be. And that's a crash tutorial, but Chapter 8 of this amazing book I'm sure you all have, I hope. Chapter 8 is a free PDF download, and that's a whole chapter on graphical models. Okay, so let me illustrate now. I'm going to pick a particular machine learning algorithm. It's called PCA, or Principal Components Analysis, and sort of something everybody learns about in sort of Machine Learning 101. And I'm first of all going to describe PCA the way you would normally learn about it from a textbook. And then I'm going to show you how to derive PCA using the model-based perspective, and we'll use those graphical models. So PCA as an algorithm is really, it's like a recipe, okay? It's a recipe that you apply to data. It first of all says, take the data. So the data will be vectors in some high-dimensional space. And there are n of them. And it says, first of all, average those vectors to compute the mean. Then subtract the mean off all of those vectors and compute this thing, which is the sample covariance matrix. then find the eigenvalues and eigenvectors of the sample covariance matrix, and then keep the eigenvectors corresponding to the m largest eigenvalues. And that, in some senses, compressed the data or projected it down onto an m-dimensional subspace in a way that preserves variance. So that's principal components as a recipe. And you can code that up, turn the handle, out would come the answer, and you have no idea why did you pick that recipe. Maybe it works brilliantly and you're done. What if it doesn't work well? What are you going to do now? How are you going to change the recipe so that it works better? So if you have no compass, you're sort of just left with random trial and error. So here's a much better way of thinking about things. So this is PCA viewed as a model. So in the same way that we're going to pick a jar and then choose a cookie from the jar, I'm going to describe to you how to generate the data, because one way of capturing your prior knowledge is to write down how the data gets generated. So in this case, it says pick a vector from an m-dimensional, lower dimensional subspace from a Gaussian distribution having 0 mean unit variance, circular Gaussian distribution. So pick a vector from that Gaussian distribution, then project it into this high-dimensional space with some linear transformation into the space of your data, and then finally generate a data point by taking that projected point, making that the center of a Gaussian distribution, another Gaussian distribution, that represents the noise, and pick a sample from that. Okay, so don't worry about the details. It's just a description of how to choose one of the jars and reach in and pick a cookie. So choose the low-dimensional vector, and then generate the high-dimensional vector by adding noise. Another little notation, it's called a plate. It says just repeat that process n times. So it says put the cookie back in the jar, give it a good shake, close your eyes again, pick a jar, pick a cookie from the jar. Do it n times. So that generative process describes how the data gets generated. It's a great way to express our prior knowledge. But when we do machine learning, we're trying to solve an inverse problem, which we have to go back the other way, which is much harder. So we observe the data, and we have to make inferences about the points in the lower dimensional space and also the values of the parameters of this linear transformation. And so we have to run inference. And then again, there's a mathematical proof that this is identical. If you run that, if you use what's called maximum likelihood to do your inference, that is, say, if you choose all the parameters to maximize the probability of the data under the model, you exactly recover PCA. Now, at this point, you think, oh, there's a lot of work just to get back to PCA. So these are completely equivalent. So why is the model-based view so much better? The reason is that if this doesn't do what you want it to do, you can go back and examine those assumptions. And you can change the assumptions to better reflect the problem you're trying to solve, and then rederive the model. You haven't just got a recipe, you've got a procedure for arriving at the best model for your problem. So we'll just take a simple example. Supposing that these draws, these generated data points, are not generated independently. So for example, let's imagine I'm air traffic control, and I want to know where the aeroplane is. The aeroplane's flying across the sky. And once a second, my radar is going to send out some energy. It's going to bounce off the aeroplane, come back, and I receive it, and I make a measurement of where the aeroplane is. Now, the problem is that that measurement is noisy. So if I just make a single measurement, I'll know where the aeroplane is roughly, but there'll be some uncertainty. Now, we know that if that's random noise, if I make multiple measurements, I can sort of average out the noise and get a more certain estimate of where that aeroplane is. So we're going to make several measurements. The problem is the aeroplane's moving. As I make these measurements, it's moving. If I just average the measurements, that'll be great because it'll average out the noise, but it'll also average out the location, which is what I'm trying to find. So that's bad news. If I don't average, if I just use the latest measurement, I won't be averaging over the motion, but I'll have a lot of noise. So what should I do? Well, you could sort of have some intuition. You could say, I should take the latest measurement, because that's where the aeroplane is, but I'll add in a bit of the previous measurement to get rid of some of the noise, maybe a little bit of the measurement before, but the measurement from 10 minutes ago is irrelevant. So I'll have some sort of, a weighted average, where I give more weight to the more recent measurements. That's sort of your intuition. Actually, that intuition turns out to be good. That's actually what you should do. but how much weight should you give? What sort of functions should you use for this decay? How much should you decay by? How do you know what to do? You're back in the world of recipes, intuition, trial and error. So instead of that, let's build a model in which we're very explicit about all the assumptions we're going to make, okay? Because that's more likely to work better, and if it doesn't, we know how to change things to improve it. So we're going to say that here's the actual position of the aeroplane in space. Sorry, this is the actual position of the aeroplane in space, the thing we want to know. We don't know, it's unknown. So the aeroplane is in some position, and then we make a measurement, and the measurement is noisy. So this is the noise process, but we know that's value. So that's the thing we observe. This is the observed position, which is a noisy measurement of the true position. Given that alone, we could estimate this, but it have a lot of uncertainty. What's going to happen now is the aeroplane is moving across the sky, and we can build a model for that. And the simplest model that we can have is to assume that the uncertainty in the position of the aeroplane is Gaussian, that the measurement noise is Gaussian, and that the movement of the aeroplane across the sky is described by a linear model. Right? So given its position and its velocity, we can compute where it will be at the next time step. Now again, we make another measurement, another noisy measurement of that next time step. And now the aeroplane moves a little bit further, we make another measurement, and so on. So that's the generative process, but now what we need to do is to run inference. We need to, given these observations, we need to compute, we need to revise the probabilities of these aeroplane locations. So again, that's sort of Bayes' theorem. It's a more complicated version of Bayes' theorem. And it turns out that that problem can be solved in a very elegant way computationally by passing messages around the graph. So we don't have time to go into that. Just a very beautiful mathematical solution called message passing. It's very generic. But this thing turns out to have a name. It's called the Kalman filter. It's been around, I don't know, the 50s or whatever. It's been very standard stuff in electrical engineering. When I was writing my 2006 textbook, I had a chapter on these time series models, and I read several books called Kalman Filters, Introduction to Kalman Filters. I found them pretty impenetrable. I mean, they're very complicated, many, many chapters before you finally get to all of this stuff. This is by far the simplest way of deriving the Kalman filter that I know. Just derive message passing in all its generality and apply it to this linear Gaussian model. And you get the Kalman filter equations, in which you say the posterior probability of this, the position of the aeroplane at this time, depends upon all of the measurements, but it's more sensitive to the current and to the recent measurements. And so you do get that decay of sort of weighting the evidence, but in a very precise way that you derive from the mathematics. And you can even pass messages the other direction, send information back in time, and get a better estimate of where the airplane was by making use of future measurements, again, as your intuition would indicate. Oh, guess what? If these are not Gaussian, but supposing they're discrete variables, again, you just pass measures back and forward. Now it's called the hidden Markov model. Well, that's a completely different literature with completely different notation and completely different but equally impenetrable derivations of how all this goes. Again, it's just exactly the same model, just slightly different assumptions. And maybe this works quite well, maybe it doesn't work quite well enough. Maybe there are some, so you try this out on your problem, you find it's still not working quite well enough, you know what to do. It could be, maybe there's a problem with the data that you've collected. Maybe there's a problem with the inference, because most inference algorithms are approximate. For the Kalman filter, it's exact, but once you get to more complex models, you're always doing approximate inference, so maybe your inference algorithm had some issues, or maybe your prior assumptions were not correct. Maybe you need to refine them for the problem you're trying to solve. You know how to do that because you made them explicit. So maybe this noise isn't Gaussian. Maybe real radar set, go and talk to a radar engineer and find out what the noise really is like and then model it. And you get better results. Okay, so I think this is more or less my final slide. What I've shown you so far is really a philosophy, a viewpoint of machine learning that I hope helps provide you with a compass to guide you through this complex morass of algorithms, but also a practical tool to use when you're building real-world applications. But in the back of our minds, we have a dream, and the dream is that we can somehow automate this. We can provide tools so that people who haven't read all the textbooks on neural nets, machine learning and so on, you need to buy the textbooks, by the way. You don't need to read them, just so everybody's clear about that, or one in particular anyway. But to save you reading all that stuff and learning all about this, can we automate it? Can we provide tools that will help democratize this approach to machine learning? And so this is the dream. So if you think about coding up inference for a complicated problem, like the movie recommender example, it's pretty complicated stuff. It's thousands of lines of code. It's written by machine learning experts who know about the modeling, know about the inference, know how to code up the inference in the context of those models. This is all complicated stuff, all written in C++ or whatever your favorite language is, compiled down to machine code, combined with the data, lots of compute happens, and you get your predictions with uncertainty. What if instead we could write a thing which we call a probabilistic program? So a probabilistic program is just a very short piece of code written in some appropriate language, which effectively describes what that probabilistic model, that graphical model describes. So it will almost say, pick one of the jars with this probability, and then for that jar, pick a cookie with a certain probability. Or the aeroplane is at this position in the sky, and 1 second later it's moved to a new position, and I'm going to make measurements. The measurements have Gaussian noise or something. It's just a simple description in a few lines of code, maybe, if we're lucky, tens of lines of code, that describes the generative process of the data. It describes, in a very clear, intuitive form, the prior knowledge that we're baking into our model. And then we're going to have a piece of magic, which is a probabilistic program compiler, which is going to take this high-level description and generate these thousands of lines of code automatically. So that's the dream. We haven't achieved the dream, but we have made a lot of progress. We've built a compiler, and if you go to infer.net, you can download infer.net, and there's lots of tutorials and examples and so on. And infer.net doesn't cover every possible case, but it covers a lot of common cases. And for those cases for which it is applicable, you do have this automation. And of course, the whole time we're looking to extend it and generalize it. So this is quite an exciting program of research. And so I'm going to leave you with this. This is the graphical model with the random variables, the probabilities, and the plates for the movie recommender problem, the problem of recommending movies. So we have, here we have users. So stand back so I can read the writing. Okay, user bias feature weight. So what we've got here are features about the user. It might be age, gender, geographical location, or something, anything which might influence what movies I like. Here we've got features of the items. So it might be the duration of the movie, the actors, whatever, perhaps genre, action, adventure, romantic comedy, and so on. And then we also have in here information, which is what we call collaborative filtering. So that's people who like this movie, people who like the movies you've liked so far also like these other movies, so perhaps you'll like them, but not coded up as some sort of hacky piece of intuition, but just described by a probabilistic model, a very precise probabilistic model. And so this can be cast in a few dozen lines of infer.net code, and then the inference algorithm can be compiled automatically. And so right down here, we have the thing we observe. That's the ratings. That's somebody saying, I like this movie or I don't, or this movie is 5 stars, this is 1 star. Once we make observations from a user about which movies they like, we send information, we pass messages up this graph, revise probabilities for all of these hidden variables, send messages back down again, and we get revised probabilities, which are ratings for movies the person hasn't yet seen. And so we update the probability that I'm going to like some unseen movie based on ratings I've given to movies I have seen, plus all the ratings that thousands of other people have given to that movie and other movies. So that's how that works. And again, that's all coded in infer.net. And so I'm going to leave you with another book. But the good news is this book is online. It's free. Will be forevermore. It's called Model-Based Machine Learning. It's written, it's co-authored with John Wynne, and John has actually done overwhelmingly the bulk of the work on this book, so I'm very much the second author. This is really John's baby. This is a very unusual book. There's a little introductory chapter, but then thereafter, every chapter is a real-world case study. And we've chosen examples from Microsoft, because that's what we know about, and these are things we've worked on. And in each case, we start with the problem we're trying to solve. We're trying to match different players on Xbox so that they'll have a good game. In other words, they'll be similarly matched in strength. That's the problem we're trying to solve. We'll then describe the data that we have. We'll describe the prior knowledge, the assumptions we're going to make. We derive the machine learning algorithm. We test it out on the data. We find it doesn't work very well. Because that is what happens in practice, right? Anybody who's ever tried machine learning in the real world, the first thing you try generally doesn't work. And then we go around and then we go back and we debug it. Was there a problem with the data that we collected? Was there a problem with the inference, the approximate inference algorithms we used? Or was it a problem with the assumptions that we made? And so we'll go in and we'll revise the assumptions and then run it again. And of course, every chapter has a happy ending. We get good results and it ships and is used by millions of people. But it's a little bit more honest about the process by which we arrived at those solutions. And it shows you how, I hope, for each of these examples, and they're drawn from very different domains, medical examples and so on, in each case, hopefully you can see how by making the assumptions explicit, that critical prior knowledge, by making it explicit, it gives you a compass to guide you through the process of revising and refining the solution and getting it to work properly. Otherwise, you're just left with in sort of a big space of trial and error and not knowing what to try next. So with that, thank you very much.
Thank you, Chris, for that great talk. And we'll probably take a couple of questions, and then, yeah. We have the mics. Okay, I saw this hand going up first. So maybe one mic for the gentleman here.
Hello, sir. I'm Shaurangshu Bhattacharya from IIT Kharagpur. Thank you for the very nice talk. So I have one question that by restricting to the class of probabilistic models, are we losing something? What is your thought on that? Because there are neural nets which are not probabilistic models.
Yeah, several thoughts on that. First of all, the probabilistic view of machine learning is a general one. So the quantification of uncertainty using probabilities is the only rational way to deal with uncertainty. In practice, we often can't deal with probabilities exactly. We generally have to make approximations. One extreme approximation is a point estimate. So we replace some complicated distribution with a single value. That single value will be chosen in some way. It might be maximum likelihood, for example. So if you're taking a neural net and you're training it by minimizing error, which is a log likelihood, a log prob under some assumed noise distribution, then you're approximating that probabilistic inference. And it may be a very drastic approximation. And for very big, the bigger, the more complex the model, the more data you have, the more performant you need to be. Typically, the more radical the approximations you have to make in order to get something that's tractable and sufficiently performant for your application. So it is quite general. Generally speaking, though, although you may not be able to maintain full probability distributions over all of the internal variables like we did in the movie example, so all the weights, internal weights of the neural net, nevertheless, the outputs almost invariably should be probabilities. So I would say as a rule, whenever you're making predictions, they should always be probabilistic predictions. I mean, one of the problems with support vector machines, it just intrinsically was not probabilistic. And there were ways of fixing it up afterwards. So when you make a probabilistic prediction, instead of saying this person has cancer or they don't, you say there's a 37% chance they have cancer. First of all, you can threshold it, and it's back to a decision. But you can do so much more. For example, maybe the cost of taking somebody who has cancer and misdiagnosing them as not having cancer is much worse than taking somebody who's healthy and diagnosing them as cancer. Because in the first case, they might die. In the second case, they might get upset and need some further tests. So that loss matrix is very asymmetric. And if you've got probabilities as outputs, you can take that into account correctly. You can use probabilities to combine the outputs from multiple systems. It's like a euro of uncertainty, universal currency that you can combine different systems. You can do things like threshold it. You can say, I'm only going to make a decision when my confidence is above a certain level. And if my confidence is below that level, I'm going to send it off to a human. So if you've got some very repetitive tasks like medical screening where people are staring down microscopes all day long, you might be able to help them by just taking 90% of the data, saying we're very confident this is not cancerous, but everything else we're going to leave to human judgment. That's a very practical thing you can do today. So lots and lots of advantage of having probabilistic predictions and no downside. So always use probabilities.
Okay, Mausam has a question, then we'll take one more. So two more questions, then we'll wrap up. Yeah.
I'm Mausam from IIT Delhi. Thank you for a very nice talk. I learned my AI in the early 2000s. And that was the time probabilistic graphical models were at their peak. And I'm an application researcher. I work in natural language processing. And I remember conferences where pretty much all the papers, except a very few, were all probabilistic graphical models based. Sometimes at some point it became LDA based and so on and so forth. Of course, there's a new world order. And so I find very few papers now in the application areas. Now, I'm not talking about people who work in the theory and the fundamentals of machine learning. There's a lot of work still going on in there, and some unsupervised learning as well. But in the application domains, it is all neural networks, left, right, and center. And probabilistic graphical models are either not being tried or I have been overtaken, and life has changed. So I want to understand your perspective on, in the future, as you know, in the times to come, what do you see as the role of probabilistic graphical models based solutions in application areas? Do you believe that they will still have a strong role to play, or do you believe that they will be overtaken by neural networks? If they will have a role to play, would it be in conjunction with neural? What is the value it will offer? When is using a PGM solution the right solution to approach?
Sure. So you've got to understand that machine learning, like everything else, it's a social enterprise, all right? So let's take neural networks. There was tremendous excitement in the 1960s around perceptrons because machines could learn, and you could cut 10% of the wires, and it carried on working just not quite as well, just like the brain. So tremendous excitement. Then it all went away again. Then it all came back again in the 1980s, 1990s. Neural nets were the solution to everything. Then it all went away again. Then it all came back again. So right now it's all... And in the application domain, we've got these particular techniques, certain classes of convolutional nets and LSTMs, and a handful of things that are working very well on certain problems for which we can collect lots of data, we can label it up by hand, many, many practical applications. So it's unsurprising that this tremendous focus of applications is bearing down on this one set of, we've discovered this new technique, and everyone's applying it in all kinds of places. That's unsurprising. If you step back and look at the field of machine learning, it's a very broad field, and this discriminative training based on hand-labeled data is one tiny corner, which has all kinds of, I think, the last speaker covered some of these. There are so many limitations, and it's scratching the surface of what we want to do with machine learning. There's a whole world of reinforcement learning, unsupervised learning, there's causal discovery from data, and somebody mentioned the work at Bernard Sherlock and others. There are all issues about bias and in learning. Think of the world of machine learning as this enormous opportunity that's out there in front of us. And then right now, there's a whole bunch of people, for understandable and good reasons, focused on using a particular technique for applications. So first of all, probabilities are at the foundation. There's a mathematical theorem that says if you're behaving rationally and you're not certain, you're going to use probabilities or something equivalent. So it's not going to go away. I don't think the maths are going to change. The graphical models are just a very beautiful notation. Personally, I find a picture is worth 1,000 equations. And it's just much easier to look at a picture and see what it's saying than pages and pages of math. So I don't think the pictures are going to go away anytime soon. But your question was really about practical applications. And there's certainly applications, and we work on applications, you'll see examples in the book, where just throwing it at a deep neural network is not the right way to go, where actually graphical models are the appropriate tool and technique to use. So I can't predict what the next wave is going to be. Maybe reinforcement learning will dig in and get some real traction. Everyone will lurch across and start applying reinforcement learning to everything. But in terms of the field of machine learning, what an amazing time to be going into the field. We're just at the beginning of this. My son's at university doing computer science, decided he's interested in machine learning, and I think, well, that's great. There's a whole career to be built in this because we're just at the beginning of this. Yeah.
But just a tiny follow-up. So you said that you tried neural networks in some applications that they didn't work. I'm really happy to hear that. But can you characterize what kinds of settings you expect neural networks to not do well where PGMs would be the right solution in a supervised scenario?
Sure. Just an example would be the skill matching example in Xbox. Again, there's a chapter in the book where, what are your assumptions? Well, you've got some players and they have some skill and you have some uncertainty in those skills, which we describe actually by the simplest possible model, just a Gaussian distribution. And then they play against each other, and then you have some model for how their performance varies, because the stronger player will sometimes lose to the weaker player because they didn't play too well in that particular game. And that's how we model all of that. And in fact, actually, if you take that model and look at just the maximum likelihood limit, where you throw away the uncertainty, you come up with something called ELO, which is the standard method used in chess worldwide. Right? So that's a model which is appropriate to that particular application. So again, it all comes down to, again, the sort of fundamental point of the talk was that there isn't such a thing as a universal algorithm. Again, there's a mathematical theorem that proves that. It's about building the right kind of solution that's tailored to your problem. So you'll see some examples of that in the book.
Okay, we'll take one last question here, second row. Yeah.
Hi, this is Ankit Anand from Indian Institute of Technology, Delhi. And I'm a PhD student there. And it is really heartening to see you talking about the probabilistic graphical models. I work in probabilistic graphical models, and at times, in these times, it becomes scary whether I'm working in the right area where the whole world is talking about deep learning. So it gives me a sense of security. First, that the person like you is propagating that. Thanks for that. So the question is basically, so you shift the onus from the algorithms to the probabilistic models and assumptions. But then when you work into the probabilistic graphical models, another question arises like how you choose, I think the same problem gets shifted to how you choose which approximate inference algorithm to choose from. Like if I work in structured prediction, there are ample amount of approximate inference techniques, variational inference to MCMC. yeah, there is some understanding on that, but I think the problem is just shifted to what algorithm, what approximate inference algorithm you will use for the probabilistic graphical model. That's the first question, and the second is at a higher level. So you talk about that there is no single algorithm as such, and you have to adapt, you have to see the problem, understand the assumptions, and then see which algorithms works there. On the contrary philosophy of, if I understand it correctly, Pedro Domingos talk about the master algorithm, which will work everywhere almost. So what are your thoughts on that?
Okay, yeah. Let me, first of all, just, I don't want to convey the impression there's graphical models over here, and there's neural nets over there, and you choose one or you choose the other. I mean, deep learning is the ability to train these deep hierarchical layered structures, and you might describe your problem by a graphical model, but maybe one of those conditional probabilities is a deep neural net. So these are not alternatives. They're more like, I think of the probabilistic framework and the graphical model as a way of, again, sort of like a compass to guide your way around the world of machine learning. Deep learning is a very powerful technique, and it's cropping up in many, many different places. We use it a lot. So I don't want to characterize them as alternatives, but I do like the graphical models as sort of a general framework for describing models. Sorry, the second part of the question was the... Yeah, okay, so... Yeah, I haven't, I mean, just for lack of time, I've said very little about approximate inference. Again, that model-based machine learning book guides you through some of the inference methods that we're using in that context. And again, in real-world applications, you make approximations, and those approximations, you know, you might have a complicated multimodal distribution, you might approximate by Gaussian, which is unimodal, and you're losing some sort of uncertainty, some ambiguity there, and that may or may not be important. So part of the challenge is, when you don't get the results you need, is diagnosing where the problem goes wrong. So making the bad assumptions, inappropriate assumptions, is just one of the places. But if somebody hands you rubbish data that isn't what it claims to be, then you can just get bad results even if your assumptions are correct. And the same thing with the inference algorithm. That's a whole very complex world in its own right. And in a sense, the goal of info.net is to hide that from you, to have you can focus as the domain expert on your prior knowledge that you know because you're an expert in medical imaging, because you're an oncologist or whatever, and you don't have to know anything about inference. And the goal, you know, the ultimate dream of info.net is the inference will be entirely automatic. And we're not there yet, but we've made progress.
Okay, I think we should wrap up for now because we're already at kind of at the scheduled end time. I'll request P. Narayan to say a word of thanks for Chris. Yeah, thank you very much. It's a great talk again. Yeah. Thank you, Chris.